Hello, myself Gautam from Group 316. Today my topic is biofluid mechanics, fundamentals of fluid dynamics. Fluid dynamics is a branch of physics and engineering that studies the behavior of fluids in motion. The fundamentals of fluid dynamics are built upon several by concepts, principles, equations that describe how fluids how interact with boundaries, respond to the forces. This is an overview of the main concepts. First one is properties of fluids. Understanding fluid dynamics begins with the properties of fluid itself. Density, mass per unit volume, often expressed in kg per meter cube. Viscosity, a measure of the fluid's resistance to flow or internal friction. Pressure, force exerted by the fluid per unit area. Temperature affects fluid properties such as density and viscosity. Compressibility determines whether the fluid's density changes significantly with pressure. Second one is flow types. Laminar flow, turbulent flow, steady, unsteady flow, compressible and non-incompressible flow. Laminar flow, it is smooth, orderly with parallel streamlines. Turbulent flow, chaotic and irregular with mixing and swirling. Steady and unsteady flow. Steady flow has a constant flow parameters over time while unsteady flow varies. Compressible flow considers the density changes, whereas incompressible flow assumes constant density. Third one is governing equations. These equations form the foundation of the fluid dynamics continuity equation. This equation describes that in any steady state process, the rate at which mass leaves the system is equal to the rate at which mass enters the system. Momentum equation. It is also known as Navier-Stokes equation. Law of conservation of momentum. It states that the rate of change in linear momentum of a volume moving with a fluid is equal to the surface area, surface forces, and the body forces acting on a fluid. Energy equation. It accounts for the conservation of energy, considering heat transfer, work done, and internal energy changes. Bernoulli's principle. It relates pressure, velocity, height in an ideal flow. Dimensional analysis and similarity. Reynolds number and Mach number. Reynolds number determines the laminar or turbulent flow, and Mach number measures the compressibility of effects. Applications. Fluid dynamics applications principles are used in aerodynamics, hydrodynamics, meteorology, medicine, and engineering. In aerodynamics, it is used for airflow over wings and vehicles. Hydrodynamics, it is a flow in pipes and oceans. Meteorology, it is for weather systems. Medicine, it is for blood flow. And in engineering, it is for turbines, pumps, and reactors. These principles allows us to predict and analyze the fluid behavior in natural and engineered systems and provides a comprehensive framework. The governing equations. The governing equations in physics and engineering describes how physical quantities interact and change over time or space. These equations are fundamental principles that govern a system's behavior and can be classified into several categories based on the type of phenomenon being studied. Here's an explanation of the key types. First one is conservation laws. Mass conservation. This states that the mass cannot be created or destroyed in a system, it only changes location or form. For example, in a fluid flow, the mass entering a region equals the mass leaving it, assuming no accumulation. Momentum conservation. It describes how the motion of an object or system is affected by the forces. It ensures that any change in momentum is due to applied forces. Energy conservation. Energy cannot be created or destroyed, only transferred or transformed. In a system, the total energy remains constant, balancing between kinetic potential, thermal, and other forms. Second one is thermodynamics. These equations describe how heat, energy, and work interact in a system. They govern processes like that transfer, phase changes, and energy conservation, ensuring the laws of thermodynamics are satisfied. Third one is electromagnetic equations. This describe the behavior of electric and magnetic fields as well as their interactions with charged particles and currents. They explain phenomena like how electric fields generate current or how charging magnetic fields induces voltage. Fourth one is fluid dynamics. These equations govern the motion of fluids and describes properties like velocity, pressure, and density. They capture phenomena like turbulence, flow patterns, and wave propagation. Fifth one is wave equation. This describes how waves such as sound, light, or water waves propagate through space and time. They connect the motion of particles in a medium to the transmission of energy. Sixth one is quantum mechanics. These equations describe the behavior of particles at very small scales, such as atoms and subatomic particles. They involve probabilities and describe phenomena like particle duality and quantum entanglement. Seventh one is structural mechanics. This equation describes how materials and structure respond to forces, stress, and deformations. They help predict whether a structure will bend, break, or remain stable under load. Governing equations form the mathematical backbone for doubting and predicting the behavior of physical systems under various conditions. Each set of equations corresponds to a specific type of conservation or interaction law, ensuring the physical world behaves consistently, predictably. And last topic is classification of fluids flow. The classification of flows is a fundamental concept in fluid mechanics that involves categorizing fluid flows based on their properties, behavior, and governing factors. The main types of flow classification. First one is based on the state of the fluid. First one is compressible flow. Fluid density changes significantly due to pressure variations, typically in gases at high velocities. Example: supersonic jet.